the definition of a very special kind of graph, which is called a tree. And first of all, we need to define that what does it mean by acyclic graphs. A graph GV having no cycle is defined to be an acyclic graph. Okay, and if you can find out a connected acyclic graph, then that would be a tree. Okay, and a connected acyclic graph is defined to be a tree. For example, this is a connected graph and it has no cycle, so therefore it is acyclic and it is connected, so it is a tree. Similarly, you can define, this is a tree, you can define, right, this is a tree. So these are all examples of trees. Okay, okay, now I would like to say that we need to introduce one important definition in this context, which is called the definition of spanning subgraph. What does it mean by a spanning subgraph? That is a subgraph. We have already defined what does it mean by a subgraph. So a subgraph G1 of a graph G is said to be a spanning subgraph if it contains all the vertices of G. Okay, so a subgraph of a graph is called spanning subgraph if it contains all the vertices of G. Okay, for example, suppose you take one okay, then this is a graph G, and you can so spanning subgraph, you can define a spanning subgraph of G. Maybe you should take all the vertices, okay, first of all, and then you take this one. Okay, so this is a spanning subgraph because it contains all the vertices. Okay, now from out of a spanning subgraph we need to construct a spanning tree. That means we is connected and we should be acyclic, free of cycles. So that means, so in this context, suppose G be a connected graph, then a spanning subgraph will be called G1 will be called a spanning tree. A spanning tree. If the subgraph G1 is a tree. Okay, that is if G1 is acyclic and connected. Okay, that means, for example, suppose we consider a graph this one. So this is your G. Then one can find out, so from this you can find out a spanning tree. So like you need to take all the vertices first, right? Then we can take this one, this. So this will be a spanning tree, right? Because this is acyclic and this is connected. Also you can take this one. Yeah, you can take, suppose so you can take this one, and also we have this, right? So this is also, suppose it is G2 and it is also a spanning subgraph which is connected and acyclic. That so can one construct a spanning tree for a connected graph? Okay, because in the above situation we have seen that yes, because this is a connected graph, this is, so this graph will give you a spanning tree, at least this one, and maybe you can find out another. Okay, so this is a connected graph, and from this graph you can construct a spanning tree out of this main graph, right? So that question is a viable question, that can you construct a spanning tree out of a connected graph? The answer is true. So it must be a theorem, so every connected graph has a spanning tree. Okay. Now what is the proof? What is the proof? So suppose you take a, so let G be a connected graph. Then what you do? Now it is a fact, if G itself is a tree, if G is acyclic, if G is acyclic, maybe it may happen that whatever you consider, it may be acyclic. So if G is acyclic, then we are done. Okay. But if not, suppose it is not acyclic, then what you will do? If not, so then there exists at least one cycle. At least one cycle in G, right? So you can find out the cycle of the graph. Okay. So what we shall do? Suppose your cycle, you can name it. So suppose C1 be your cycle, be the cycle in G. There are many, but we just start with this cycle C1. Okay. Then what you will do? So in this cycle, you need to delete one edge from the cycle. So you are going to delete one edge as per your choice from the cycle. Okay. Then the remaining graph, then still the remaining graph still connected, right? So suppose you just denote it by G1. Now then what you will do? Now check whether G1 is acyclic or not. If it is acyclic, then you are done. If not, then there exists another cycle in G1, right? Then again you delete some edge from that cycle and you will get another connected graph. Okay. And if the remaining graph still connected and acyclic, then we are done. If it is not acyclic, then again you need to proceed. Okay. So you can continue this process of finding a cycle and deleting one edge from your choice from the cycle until and unless you will arrive at a graph that has no cycle but still disconnected. Okay. So continue the process. Okay. So certainly you must get a connected graph which will eventually be a connected graph having no cycle. Okay. So therefore that connected graph will be a spanning subgraph which is acyclic. So therefore it is a tree. So this proves the theorem. Okay. Now let us define a just one definition, that if you want to take a collection of trees, then that will be called forest. Okay. Okay, and it should be remarked that that a spanning tree is always connected. A spanning tree can be defined only for a connected graph. Okay, because a tree must be connected, right? A tree must be connected, and also in a disconnected graph, having suppose m many vertices, okay, in a disconnected graph having m many vertices, one cannot find out a connected subgraph. A connected subgraph of m many vertices. Okay. Okay. Now, secondly, each component of a disconnected graph however, does have a spanning tree. Each component, right? So, since components are connected, so in a disconnected graph there are many connected graphs, so maximal connected graphs, so therefore they are called components, and each component will have a spanning tree. Okay, so that means, so this shows that a disconnected graph with k components has a spanning forest, right? Forest of k components, because in each component you will find out a spanning tree, so therefore you have a collection of trees, so therefore it is a forest. Okay. Now, how do you find out that, on checking, that the given graph will be a tree? There must be some condition through which you can say that the given graph will be a tree, okay, which is evident from our next theorem, that suppose you take a graph, so a graph will be a tree if and only if any two vertices u and v are connected by a unique path, unique Suppose if you take this one, okay, so this is a connected graph which is acyclic, so therefore it is a tree. But if you check that, if you take any two vertices, then there is only one path in between them. Okay, so what is the proof? So suppose, so let T be a tree, so being connected for a pair of vertices u and v, there exists a path, there exists a cycle, I am sorry, there exists a, okay, yeah, since it is connected, so there exists a path, right. So there exists a path in between u and v, okay, right. Okay, now we need to check that there exists exactly one path. So the uniqueness part is very easy to check, because suppose you take, so suppose u and v connected through two paths, say P1 and P2, okay, then essentially their union P1 union P2, so that must be a cycle, that must be a cycle, but this is a contradiction. Okay, so there exists a unique path in between u and v. Okay, conversely, suppose the condition holds, okay, so our claim is that G has no cycle, because through the condition you can always say that G is connected, because any two vertices will be connected through a unique path in between u and v. So therefore G is connected, so you need to show that G has no cycle. Okay, if not, then there exists a cycle in G. Okay, now suppose that in the cycle, suppose that u and v are on the cycle. Okay, now since u and v are on the cycle, so u and v can be connected through two different paths in the graph. So u and v will be connected through two different paths two different paths in the graph. Okay, which leads to a contradiction to the hypothesis. Okay, so this completes the proof. Okay. Okay, so this is a very nice kind of theorem through which you can always check that whether the graph is a tree or not. But apart from this theorem, the next one will be more efficient and more effective in checking of a graph to be a tree. Okay. So what is the theorem? It's a very nice observation. Now if you check this example, okay, now this graph has how many vertices? 1 2 3, so 1 2 3 4 5 6 8, right? And this is a tree because this is connected and acyclic. Now if you check the number of edges, then you will see that this is the number of edges is 1 2 3 4 5 6 7, so this is 8 minus 1. So could it be possible to deduce that for a graph of connected graph of n vertices, it will be a tree if and only if its number of edges is n minus 1. Okay, the answer is yes. So a connected graph G of n vertices will be a tree if and only if it has exactly, it has, I do not want to specify exactly, it has n minus 1 vertices, n minus 1 edges. This is the theorem, and through which you can easily check that whether the graph is a tree or not. So this theorem is very much effective and it's a workable scheme of checking a tree. Okay. What is the proof? So we need to apply the induction on the number of vertices. Okay. So let G be a tree. Now the statement is true if number of vertices n. Okay, if the statement is true if n is 2 3, because of this, because any graph of any tree of too many vertices will be represented as like this, and any graph of 3 vertices which will be a tree if it looks like this. Okay. So therefore their number of edges are the number of vertices minus 1. Okay. So suppose that So suppose that the theorem is true, the theorem is true when the number of vertices of the tree is less than n. Okay, and now let G be a tree with n many vertices. Okay, with n many vertices. Okay, now so consider an edge UV in G. Okay, now we have already seen that any two vertices in a tree will be connected by exactly one path. Okay, so let's delete UV, okay, from the tree. Then the result is two disconnected graph, because in between U and V, so U is a vertex and U and V are adjacent, right? So that is why you are writing this as UV, edge UV. So therefore, if you delete that edge, then the graphs will be disconnected. Okay, so let's delete UV, then the graph will be disconnected. Okay, and once it is disconnected, then the two graphs that you are getting out of this, they are going to be a tree. Disconnected and let G1, G2 be two trees out of this. Okay, now then the vertex set, suppose V is the vertex set of G and V1 is the vertex set of G1, V2 is the vertex set of G2. So therefore V1 union V2 is V, and not only that, this is phi. Okay, now since these graphs G1 and G2, they are having the number of vertices which is less than the number of vertices of the graph G, that is less than, strictly less than n, and you have already assumed that the theorem is true for every graph having less than n many vertices. So by hypothesis, the number of edges in G1 must be the number of vertices minus 1, the number of edges in E2 must be number of V2 minus 1. Okay, now since E will be the number of edges of the main graph G, so E is the number of edges, so therefore it is it must be number of edges in G1 plus number of edges in G2 plus 1, because you have already deleted one edge UV, so you should include that edge to count. Okay, so therefore it is mod b1 minus 1 plus mod b2 minus 1 plus 1, so therefore it is mod b1 plus mod b2 minus 1. Now what is mod b1 plus mod b2? Since their intersection is phi, so therefore this is actually this. So this proves the necessary part. Okay. So this proves the necessary part. For sufficient part, the sufficient part is too much easy, because if you take a connected graph for converse part, easy to check. Easy to check, because if you take a connected graph G for which the number of edges is n minus 1, where n is the number of vertices, then you must show that a graph is a tree. Okay. Then what you do? Now since every connected graph has a spanning tree, so therefore you consider a spanning tree of this graph. Okay. Now since the suppose your spanning tree is T, so since T is a capital T is a tree, so by the previous part, that is necessary part, you can always say that the number of edges of T must be the number of vertices minus 1, that is n minus 1. So since T is a subgraph of G and has the same number of edges as that of G, so therefore T must be G and G is a tree. Okay. 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 Now next theorem shows that suppose you take a graph with n vertices is a tree. So a graph with n vertices is a tree if and only if it is acyclic and has n minus 1 edges. So a graph with n vertices is a tree when only if it is acyclic and has n minus 1 edges. Okay. So what is the proof? So let GV be a tree. So since it is a tree, so it is acyclic, and from the previous theorem you can prove that the number of edges is number of vertices minus 1. Then we are done. Conversely, let GV be a graph, be an acyclic graph so let GV be an acyclic graph having n minus 1 many edges. Okay. In order to show that it is a tree, we have to show that it is connected, and that's enough for the proof. So if possible, let G be disconnected. Okay. So if possible, let G be disconnected and has k many components. K many components. Suppose say Gi, Ei, Ei. Okay, for all I equal to 1 to k. Now since G is acyclic, then being subgraph, these Gi's are also acyclic, and since they are components, so they are connected. So therefore, so each Gi is then each Gi is a tree for all I 1 to k, and not only that, the number of vertices of V of the graph G must be equal to the sum of the number of vertices of each component, that is Vi. Okay. So therefore, the number of edges is summation one to k. This is I, Ei. So that is summation okay, and therefore if you take the sum, so this is actually mod V minus k. So this is a contradiction. Okay, so this is a contradiction because this is your n minus k, okay, which is strictly less than n minus 1, but you have already assumed that the number of edges must be n minus 1. ঠিক আছে, বোঝা গেছে? Okay. So yeah, so let's move to define another concept of minimally connected graph. What does it mean? So a graph is said to be called minimally connected if number 1 if it is connected, and number 2 deletion of any edge from the graph. Leaves the graph disconnected. Leaves the graph disconnected. Okay, and you can have this result that a graph is a tree. So there is a relationship between these two concepts, that of a tree and of a minimally connected graphs. So a graph is a tree, so it is evident to you that it is minimally connected. A graph is a tree if and only if it is minimally connected. Okay. Another problem, you can prove on your own that every tree must have at least two vertices of degree 1 are called leaves. Okay, called leaf. ঠিক আছে, এগুলো পড়ো ভালো করে, ঠিক আছে। তো ট্রিটা তোমার মোটামুটি হলো। হ্যাঁ, এই জায়গাতে আর সেরকম কিছু নেই, এগুলো একটু অ্যাডভান্স। আরো কয়েকটা আছে, একটা দুটো থিওরেম আছে অ্যাডভান্স লেভেলের। ঠিক আছে, এই পর্যন্ত তো পড়ো, ঠিক আছে।